Hello, welcome back. So in this video, we're going to take a look at concavity and inflection points. So we're going to see in this video how the second derivative can be used to tell us more about the graphs of functions and the behaviors of functions and get us some good information in some applied settings in future sections. So we already in section 4.3 discussed the relationship between the algebraic sign of the derivative, that is whether it's positive or negative, and information about intervals on which a function is increasing or decreasing. And also about the nature of critical points. We found that we could decide if a critical point is a relative maximum, a relative minimum, or neither by looking at the first derivative. So here's a picture of a function we may have looked at. This is kind of complicated, would have been a hard one to analyze, but here's the graph of y equals f of x equals minus x plus x squared sine of x. And in our analysis for section 4.3, if we wanted to know where the function was increasing and decreasing, we would have found its derivative, which I haven't written here. Then we would have first of all found the places where the derivative is equal to 0. And of course, we know that corresponds to places where the slope is 0. So here is a 0 slope point up here. And the derivative, the value turns out to be, for the x, minus about 2.22. Another place where the derivative is 0 is at 0. That corresponds to the flat point you see right about there. A third place where the derivative is 0 is at 1.06. That's right there. You can see there's kind of a flat spot in the graph about here too, kind of subtle, hard to see that. 2.41 corresponds to this slope 0 point, and 5.12 to this one. Okay. So if we wanted to analyze increasing decreasing for this function, we would first of all find out these places where the derivative is equal to 0. There are 5 of them. I found those with the help of a calculator using a technique called Newton's method that we'll see later on in this chapter. And then once you have those 0 places, all 5 of them, you just tried to determine what was the sign of the derivative in each of these intervals. So we found f prime negative to the left of minus 2.2 here, and that meant the function was decreasing, as we see here. And then between 2.2 and the next 0, the derivative 0, it turns out f prime is positive, so the function increases and so forth. So that's just a quick review of how we used zeros of the derivative and the sign of the derivative to inform us about where a function is increasing and decreasing. Now, the approach for using the second derivative to find out about concavity is very similar. So one of the features of graphs that often translates to important information is how that graph bends. The bend is often called the concavity of the graph, and it's related to the second derivative. So in particular, we're going to be looking at talking about where the function bends up like it does here, bends down like it does here, and also looking at places where it might change from bending down to bending up. So we start with some definitions. So the bend is called the concavity of a function. And so let's suppose we have a function defined in an interval I. We say it is concave up on the interval if its graph bends upward. Okay. So a lot of people say these graphs are smiling, so anything that goes up like this, sometimes they say these graphs hold water in some respect, those are called concave up. There's an analogous concept called concave down, and such graphs bend downwards, something like this. And again, you might think of this, if you poured water on a graph like this, it would tend to run off, like on a sloped roof. So anything bending down is concave down. Over here in these graphs, if you poured water on them, it would likely collect in some low spot down there. Or you might think of them as smiling and frowning. Now, for more insight into concavity, we can consider the tangent lines to a graph. So here's a concave up graph, one that we saw on the previous page. We're going to draw in a few tangent lines. So there they are. So we've drawn in 4 tangent lines to this graph, and we see that as we move from left to right along the graph, Here a tangent line is negative. The next tangent line we drew is positive, still pretty shallow, and then positive again but steeper, and finally positive again and very steep here. Okay. And what I want to notice here is that we move along the curve from right to left, the slopes of these tangent lines increase. That is, they go from negative to positive, and the positive slopes get even steeper. Okay. Now, the slope of the tangent at a point x is the derivative. So if these tangents are getting steeper, that is, if the slopes are getting bigger, then the derivative f prime is increasing. Now, increasing is a good word because we know something about increasing functions. So what this means is this. Because f prime is increasing, its derivative, and a function f prime has a derivative, its derivative is positive. So if we look at f prime prime or f double prime, that will be bigger than 0. Okay. So again, this doesn't mean the function itself is increasing, but the derivative is increasing, and the concave up leads to that naturally, because as we draw these tangents to the graph, we see they get steeper and steeper as we move from left to right. And again, increasing slope of the tangent means that f prime is getting bigger because f prime is the slope, and so its derivative turns out to be positive. So we're going to use this idea. We're going to associate concave up with a positive second derivative. So just as the sign of the first derivative was important in determining where a function's increasing and decreasing, the sign of the second derivative is going to be important if we want to talk about concavity. If the function's concave down at an interval, we can do the same kind of analysis. Not surprisingly here, we see the tangent lines do something different. So once again, we start drawing these tangent lines. They start off over here as positive. The next one's negative and shallow. And then we see as we move to the right, these tangent lines get steeper and more negative. So in this case, these slopes decrease as we move from left to right. And again, because the slope of the tangent is the derivative, that is f prime, this means that if the slopes are decreasing, then f prime is decreasing. So f prime decreases for a concave down function. And in fact, f prime decreasing is how your book defines concave down, although we took a different approach just looking at the pictures and seeing how it bends. But as we said before, okay, in this case, it's f prime is decreasing, so its derivative, which is f double prime, must be negative. So there's the analogous result for the second derivative and be negative that goes along with the concave down. So if we put these two parts together, we have second derivative analysis for concavity, and we're going to practice this in an example in just a moment. If f double prime is bigger than 0 on an interval I, then f is concave up on that interval, so we will know to draw the graph bending upwards. And if f double prime is less than 0 on an interval I, then f is concave down on the interval. So if the second derivative of f is negative, we'll know that we should be drawing the graph bending downwards. So let's take a look at an example to see how this works out. So let's consider the function given by f of x equals x squared minus x e to the x. The polynomial times the exponential. Both of these are nice functions. They're continuous and differentiable. So f is also continuous and differentiable. We'll focus on finding the intervals in which f is concave up and the intervals in which it's concave down. We'll also find coordinates of all the inflection points for f. We'll talk about inflection points, kind of define them as they come up, but an inflection point is just a point where the concavity changes. So we need to investigate the second derivative to talk about concavity, and to get at the second derivative, we have to do the first derivative. So the first derivative is a product rule because this function f is a product. Can't ever forget about the product rule. These derivative rules always come up. Don't forget about them. So this is the function x squared minus x times the function x. So the product rule looks like this. derivative of the first function times the second plus the first function times the derivative of the second. We're just differentiating a polynomial and an exponential here, so these are pretty easy derivatives. And we're going to simplify in this case. There isn't much to it, but factor the e to the x out and add the remaining polynomials to come up with this form for the first derivative. This is a case where we do want to simplify because we want to go ahead and compute the second derivative, and that's easier if we've simplified things first. So f prime is also given by a product, a polynomial times the exponential, so we need another product rule to compute f double prime. So that product rule again is spelled out here. We take the derivatives in this case, and again simplify because we want to work with the second derivative, find out where it's positive and negative. So factor out the exponential, and then add the resulting polynomials that remain there, and we come up with x squared plus 3x times e to the x. So we now have the second derivative. Our next goal is to figure out where that second derivative is positive and where it's negative. And in this case, we work very much like we did with the first derivative when determining where a function's increasing, decreasing. If you want to know where a function's positive and where a function's negative, like this second derivative, the best thing to do is first of all find out where the function is 0. Okay. So we want to find the places where f double prime of x is equal to 0. So this is not a hard equation to solve. F double prime of x equals 0 tells us that x squared plus 3x times e to the x is equal to 0. We have a product here, and a product is 0 only when one of the factors is 0. Because e to the x is never 0, we know that this product will only be 0 if the x squared plus 3x is 0. So we can focus on that. And a quadratic like this is easy to solve by factoring. We see that x must equal 0 or x must equal minus 3. Now, as was the case when we analyzed first derivatives, we now plot these zeros on a number line. Here's the minus 3, one of the zeros of the second derivative, and here's the other 0, which turned out to be at 0. And these zeros then cut or partition the x-axis into 3 intervals. The first one minus infinity to minus 3, so that's everything to the left of minus 3. Then we have the part between 0 and 3, and then the part to the right of 0, that is from 0 to infinity. Now, because we already have all the zeros of the second derivative, we know that the second derivative cannot change sign, for example, in this interval. If it went from positive to negative, or negative to positive, then it would have to cross the axis and be 0, but that doesn't happen. So it's enough to check or just test one value in the second derivative from each interval. So we'll check the value minus 4 in the first interval, minus 1 from the second, and 1 from the third. And whatever those signs tell us will be the signs of the second derivative on those complete intervals. Okay. Let's start on the left. Remember, our second derivative was f double prime at x, given by x squared plus 3x e to the x. So we're going to put the numbers, values minus 4, 0, or minus 4, minus 1, and 1 into this second derivative. So here we've put in minus 4. There's the substitution there. Replace the x's by minus 4 from this second derivative. And the calculation gives us 4x to the minus 4th, which is positive. So we conclude f double prime is positive on this whole interval from minus infinity to minus 3. Next, we plug in minus 1. This gives us information on this second interval from minus 3 to 0. Plugging minus 1 into the second derivative, doing the calculation, we get minus 2e to the minus 1. That's negative, and so this tells us f double prime is less than 0 on this interval. And remember, a negative second derivative means concave down. Finally, in the third interval, the easiest point to substitute is 1. If we put 1 in for x in the second derivative, as we did here, we come up with 4e, which is positive. So f double prime is positive on this last interval, and that means the function is concave up. Now, an inflection point is a point where the concavity changes from up to down or down to up. And we can see that that happens at -3 and at 0. So let's determine those inflection points right now. Okay. Now, for inflection points, we want the coordinates of those points. Those are coordinates on the graph. So we're going to have to now put the x coordinates for the inflection points, that is -3 and 0, into the function f. Remember, f of x was given by x squared minus x e to the x. So to determine the inflection point at -3, which is where the function turns from concave up to concave down, we put -3 into the f function. So the coordinates of that inflection point are -3 f of -3. So we see here. So -3 for the first coordinate, and here is -3 put into the equation for f down here. And the algebra or the arithmetic gives us -3, 12 e to the -3. So there's the coordinates of one inflection point. The second place where the concavity changes from down to up is at 0. So 0 is a point of inflection. And the coordinates of that point on the graph are 0, f of 0. And plugging 0 into f gives a value of 0. So there's an inflection point at the origin. So if we take a look at the graph of this function, here it is. There's the graph of x squared minus x e to the x. We've also plotted the two inflection points. Now, of course, we could have graphed this function on our calculator and seen something like this, which is great. And we can also, even from the graph, see a lot of the nature of the concavity. We can definitely see the concave up over here. A little hard to see the concave up here, but it is bending slightly upwards. And of course, here's the concave down part between -3 and 0. But if it was important to know exactly where that concavity changed, really can't do that without calculus, looking at the second derivative. And that tells us, even though we can hardly see any bend here, that we know the graph is bending slightly up to the left of -3 and then starts bending slightly down to the right. I'm going to throw on one last thing about second derivatives here. It turns out the sign of the second derivative, in other words, plus or minus, can in some cases tell us about the nature of a critical point. Say at x equals c. Now, this only works with critical points that arise with f prime of c equals 0. If it's a critical point where the derivative is not defined, the second derivative test is useless. But if f prime of c equals 0, and hence that's why c is a critical point, we know that then the tangent line to the graph of y equals f of x at that point is horizontal. So let's start by drawing in that horizontal tangent. So there it is. We haven't filled in the graph yet, but whatever the graph is, here's the horizontal tangent at the point CF of C. So the graph's going to go through that point. Now, suppose we've gone ahead and computed the second derivative. Okay? And it turns out that we know that that second derivative turns out to be positive at C. Okay. Well, a positive second derivative indicates that the graph is concave up. Now think about it a moment. If the graph has to go through this point and has to be concave up, it has to bend like this. It goes to slope 0 here. It has to bend back up. So if this happens at a point where the tangent's horizontal, you have no option but to have a picture looking something like this, which means that you really have a relative minimum at this point. Move on to the next slide. You see the official picture. There it is. That's what the positive second derivative means. We have concave up near the point CF of C, and that can only mean that that horizontal tangent corresponds to a relative minimum. And of course, for second derivative negative, similar things happen. If the second derivative turns out to be negative at c, then the graph is concave down. And again, if we want a flat tangent and concave down, the graph cannot go through something like this. And it can't do something like this. Those both violate the concavity. It has to go something like this. And so that means if we have a negative second derivative at c, we have a relative maximum. So the second derivative can be used to determine the nature of critical points. But again, it's kind of restricted in its use. This only works for critical points that arise because f prime of c is 0. Doesn't work at those where the derivative doesn't exist. And if f double prime equals 0, there's no information. You can see in your book that in those cases anything can happen. But when you bring all this stuff together, we have the second derivative test for classification of critical points. So again, this works if we have a point where f prime at c is equal to 0. So c is a critical point for f. And the second derivative test, the important parts, the useful parts are down here. If f double prime of c is positive, then c comma f of c is a relative minimum. And if f double prime of c is less than 0, then c comma f of z is a relative maximum. The reason I tend to stay away from this test, again, is because it doesn't always work. It only works for certain kind of critical points and only works if that second derivative is non-zero. So if you get into a position like this, where f double prime c is 0, the test gives no information. You might have a relative maximum, you might have a relative minimum, you might have neither. There's no way to check just from the second derivative, so you just have to go on and try something else. Usually I'd go back and try the first derivative test, which always gives information that you can use. Okay, so we're going to conclude here and kind of preview our next video. So we've been studying a lot about calculus in the recent weeks. We've studied limits and the derivative and learned how limits and derivatives tell us various things about the way functions behave. So we use limits to investigate horizontal and vertical asymptotes, among other things. We use the first derivative to find critical points, determine monotonicity, that is where a function is increasing or decreasing. We can use the first derivative to even classify those critical points. The second derivative tells us about concavity, as we just saw, and inflection points. Those can be important points in certain kinds of engineering and physics analysis. And then you brought a lot of old skills with you into the calculus. You know how to find intercepts. That I mean x and y intercepts, places where graphs cross the x and y axis. You know about finding the domain of a function. You have a lot of knowledge about functions you bring with you, about what exponential functions look like, graphs of quadratics, trig functions, and so forth. Now in the second video for this section, we're going to see how we can bring all of these tools and techniques together and do a real bang-up job drawing graphs and understanding a graph. So I hope you'll join me in the next video where we look at a graph in great detail.